the webinar. Thank you for your interest and joining on time. Okay. First, we have this agenda for today. We will introduce the project chairs and briefly talk about how iNEMI project is established, is developed. And then Chongken will introduce the project, introduce the earlier work of phase 1 of this project, then talk about the second phase, what will be covered and the timeline. I will explain how to join this project, and we will open for Q&A at the end. Okay, next. So we have 2 chairs for this project. Chongken Oi is from Intel. He's a senior assembly and packaging analyst. He has a master's degree in mechanical engineering, and his expertise is mainly in thermal and fluids analysis, in packaging assembly process development, and also the thermal management. Wendy Xu is from Celanese. She is a manager for design and the CAE team. She has been working on the simulation and also managing the design team at Celanese for over 10 years. She has a master's degree in polymer material and engineering. Okay. Next. So for iNEMI, I think some of you are already familiar with this. We have several steps. Basically, for each of the project, we will go through those stages. A project will start from a concept with a proposal of idea that will satisfy the needs from members and the industry. Typically, it solves a common issue that we see need collaboration across the supply chain. It typically not, it could be challenge for individual company or just to work with your partner to get through. It typically involves different segment of the supply chain. Then once we have a proposal or concept, we will get into the define the scope, the objective, what we want to accomplish, the expected outputs, and also identify who are the key players we need to should invite into the project for discussion. So during the definition and the planning, we called it initiative stage. It's open for the industry input so that we can have a project properly defined, especially for a new area. We need to involve members and non-members so that we make sure we have a good project that will bring value, it's meaningful for the members and the industry. So during the planning, we will have a detailed project statement of work and project statement agreement established so that companies who are interested will be able to make a decision and review to decide if they will join the project. So that's a baseline for a project to move ahead. Then we will, after the technical committee review and approve the SOW and project statement, the project will enter a launch stage. This is where we are currently in. We will organize, like the webinars we have today for the call for participation, and we communicate and with the industry, some players to see if they are interested. Even though for a continuous project we have relatively mature participants from the earlier phase, but we expect to have more engagement or participation from the industry so that we can bring in new ideas, thoughts, and it can benefit to the larger group as well. So once we have the sign up finished, we have committed members to join this project as a participating member. So we will start the project execution and accomplish all the goals and the plans as defined in the SOW. So during this stage, the project is limited to the committed members who signed the project statement. Once the project goals are achieved and we accomplish the tasks, we will report at the closure stage to communicate what has been accomplished, what's the major learning and lessons learned and findings, what would be the next step of future work, some gaps or recommendations to the industry. So this will call the end of the project or a phase of the project. Okay, next. So as mentioned, we have two documents governing for the project. One is the statement of work. It defines the project scope, background, the objectives, and what's needed resource, materials, etc., and also the detailed schedule, tasks. We have another document called Project Statement Agreement. This document need to be signed by companies who want to participate. This is to secure the commitment on the resource and also the terms defined for the project management and also complying with iNEMI bylaws. So as mentioned, for the project execution after launch, this project will be run in a closed group. The iNEMI membership will be required. This is to provide a legal framework so that companies who join this project, they don't need to sign additional NDAs and some other documents, but they comply with iNEMI bylaws and they agree with the iNEMI IP policy and the project management rules. So those are already defined in the membership legal documents and also the project statement specifically for this project. Okay. Those two documents are available on the project website. I will have that link shared later. So I think that's all I would introduce for this project. I think we have a next slide. Yeah, describe who has been contribute to the project, this phase 2 planning. Those are the, in fact, those companies are the members from the phase 1. They would expect it to be continue with the second phase as well. We just take the chance to thank their contribution and their effort. Okay, with that, I think we will move to the project briefing, and I will hand over to Chongken. Chongken, please.
Okay, thanks, Haley, for the project introductions. So I would like to take over to share about the project briefing. So first of all, I would like to provide some background and key challenges in this large socket Warpage analysis. So the picture here is basically showing you the high density interconnect CPU socket. So typically you can find this socket right for the desktop and also the server motherboard. Right, so it actually serves as an interconnect between CPU to the motherboards. And we do see it increasing in the trend in terms of pin count. So this indirectly will enlarge the package form factor to become bigger and bigger. Right, so that imposes some key concerns and challenges, right, when we talk about the socket Warpage. And as a package size become larger, right, so majority of simulation completion time actually consumed by the flow analysis in the pinhole regions. So as you know, as the pinhole become larger, right? The mesh count or the mesh density for these injections molding simulation become challenge, right? And so there are a few key challenges that we address, right? So the first one would be if we're able to find a solution that can speed up the simulation time or achieve a reasonable accuracy as compared to the complex pinhole design, right? And also to understand the fiber film material sensitivity to warp. And the third one is the impact of the socket design and process condition to the socket warpage. So from here, you can see that actually the we put right the impact of the socket warpage into three major pillars, right? So the first one will be the material set, then followed by housing or the geometry design, and the final one will be process conditions that refer to the injection molding process, right? Be it the temperature, cooling temperature, injection temperature, and also the ejection temperature as well. So this is the picture of the filling pattern or the flow fund or validations by our partner, right, which is a Modex 3D. So the top portion is the actual build, right? So the filling at different stage then is compared against with the simulations of validations. So this is just to give you an idea, right? So how the filling pattern can be validated with the modeling. Then this again, we'd like to highlight the phase one team member. So we have a similar team member, right, carry forward from phase one to phase two, right? So I would say not all of them actually continue to phase two, but I would say a good fraction of them actually continue to phase two, right, to further work on this particular project. So this is recap or the summary from phase one, right? Has been what's the key learning and observation from phase one. So far for phase one, the team has developed or established an analysis and validation framework for this socket development, right? And also they have built the socket and conduct some measurements, right, in order to validate the room temp warpage between modeling and the actual measurements. Right. And also to understand that how is the socket design impact to the warpage. For example, core and without core out design. So how does that impact the package warpage? And also from the effort to speed up the simulation time, right, by using a simplified approach. Right, the team have observed that a significant increase in terms of efficiency or reduce the simulation time by using a simplified approach, and at the same time achieve a reasonable accuracy as compared to the complex or the original model. Right? And also, we do see some gap in terms of the room temp warpage prediction. So that will bring us to further investigate, right, the material property for the LCP material in order to improve the predictions accuracy. So this graph actually just illustrate the concept. For example, the red line here is a simulation time, right, needed for different design A to E. So if we just directly simulate the actual socket, so it's going to be very time consuming. So it depends on the package form factor and also the pin count. For some certain cases, right, the simulation time could be from 8 to 12 days, right? It depends on the complexity. So it's very time consuming. And if we introduce the simplified approach, right, so you speed up the simulation time, right, and while giving us a relatively good trend as compared to the actual model. So that will cut down the simulation time and enable faster assessment. Right. So at the end, while we lock down the best design, then we can explore the option to use the detailed pinhole design, right, to further investigate, right, the impact to the warpage. Then the next is about the LCP material. So this one will basically talk about the benefit of LCP material that used for this socket design. So LCP is stand for liquid crystal polymer. Right. So this liquid crystal polymer in particular offer few benefit over others material set. Right. So the first one would be high flow ability. So from this spiral flow test, we can see that the LCP actually have higher flow ability. So which means you're able to fill a tiny gap without any major concern. And the second one is no flash. So this actually will enable faster cycling. And the next one will be the dimensional stability. Right. So LCP offer a good dimension stability because of its lower CTE and lower water absorption. So it will guarantee dimension stability, which is good, preferred for manufacturing. And the third one is the SMT process agility, right? And from this chart, you can obviously see that LCP has a highest HTT temperature as compared to other material set. And the final one is the dimension is very dimension precision. So it offer a very good dimension precision, right? Because the volume change from liquid stage or molten stage to the solid stage is very minimum. So this to highlight, right, 3 set of LCP material that has been selected since the phase 1 activity. And these 3 set material will be carried forward into phase 2, right, because we need to have a further study to understand the material behavior to the warpage. So these 3 set are Vectra, right, 4AI, Vectra Fit 30, and Zenite 5145L. So from the filler standpoint, both of these have 43% glass and material mineral, and for Zenite is 45% glass. So both of these actually have a high flowability and low warpage, right? And Zenite in particular is have a very good well-line strength. So that's the reason why these 3 material has been selected in order to understand the impact to the warpage. Then this page will share about the simplification effort that has been carried out. The whole objective is to reduce the simulation time while maintain a reasonable accuracy as compared to the complex or the complicated pinhole design. So for this, in phase 1, the team has choose this kind of socket LGA, right? So 61 by 51 dimension to begin with. So the idea is to keep the geometry, the same socket geometry, while reduce the surfaces for the pinhole in order to improve the simulation time. So as you can see that this is a pinhole design for the original model. So it consists of 18 surfaces per pinhole. And the simplified model 1, by using cylindrical, reduced to 1 surface per pinhole. And the simplified model 2, reduced to 4 surfaces per pinhole with a square geometry assumptions. Then this is a total solid mesh count, right? Comparing the mesh count that can be improved or reduced, right? If we use the simplified approach. So in this particular model, right, we have without call out and with call out. So in general, we do see a significant reduction in terms of mesh density, right, by using the simplified model 1 and 2, right, because the number of surfaces has been reduced significantly. And in terms of the simulation time or the CPU time, we do see a significant improvement as well, right? So for example, for case without call out, right, we can see roughly 2x improvement. And also for the case with call out, right, we see more than 5x improvement in terms of the simulation time. So beside the simulation time, we also observe that some additional benefit by using the simplified approach. Right, so it actually indirectly will reduce the file size, so make the file transfer import become easier, right? Then you speed up the simulation time. So on average, we see observe about 67% improvement over the original model. Right, so this is a whole purpose to simplify the geometry from the original model. Then the next one is the filling pattern validations or the for-fun comparisons between the simplified versus the original model. And again, we do have the two types of the socket design, without call-out and with call-out. So this is a filling pattern at 70% fill. So from this comparison, we can see that simplified model 2 actually predict a quite close approximity as compared to the original model, right, for both with and without call-out design. And we do observe that model 1, right, is slightly over or under predict, right, the filling pattern as compared to model 2 or original model. So this is reason because the pitch, the gap between this pinhole, right, cylindrical pinhole is actually larger with the cylindrical assumptions. So thus it reduces the flow resistance, and also that's the reason why it caused under predict or over predict of the filling pattern with the model number 1. So from this study, the team has concluded that we will use the model 2, right, to simplify the pinhole geometry. Then after we completed the filling, then the next step is to predict the socket warpage, right, before right after the part being ejected to the room temp. So that is also the key concern, right, because the warpage of the socket also influenced by the process and also the material set. So our partner has carried out this socket warpage analysis, right? So it's from Modex. So the effect of the socket warpage actually is a combination of two major factors. Right. The first one is random fiber orientations, which means the fiber distribution inside a socket is assumed to be randomly distributed. And the second one is fiber orientation effect displacement, which means that you consider the effect of any isotropic of the fiber orientations. So whether the fiber is in the flow arrangements is in the flow direction or in the perpendicular to the flow direction. So that will impose an anisotropic material behavior that eventually will impact the package the socket warpage behavior. So from this modeling comparisons, right, without call out and with call out, we do see that for the design that have a call out actually reduce the socket warpage at the runtime as compared to the socket without call out. So with that, I have concluded the phase 1 summary, right? Hopefully that will give an audience a good idea on the activity that has been achieved in phase 1. Then moving forward, I'm going to talk about the project phase 2 objective and the scope. So phase 2 is basically an extension from phase 1, right? So whatever gap that we observe on phase 1, right, will be further carried on into phase 2 to conduct a detailed study. So the first one is to enhance, right, the socket modeling capability, right, and also the material characterizations to predict the filling pattern and warpage behavior. Because we do see some gap, right, from the phase 1 into our room temp warpage prediction between modeling and also the measurement data. And also to characterize the impact of molding and design on larger socket. And the third one, to develop a guideline, right, for these socket warpage measurements. And the scope is basically, we'll have a larger scope when we move to phase 2. So in phase 2, we'll cover and focus on both room temp and high temp socket dynamic warpage, right? Because eventually the team are interested to understand that how is a socket warpage when it's subjected to the referral process. So basically, we reuse, right, and the sample build that we already built completed in phase 1. So and that sample will be sent to our partner for the dynamic warpage measurement and also compare against with the modeling that we have. Then the next one is seeing we observe a warpage prediction gap at room temp from phase 1. That's why we would like to look into this anisotropic behavior of the resin of the LCP. Hopefully, we can improve the socket warpage prediction in both from them and high temp after consider the anisotropic effect of the resin property. And also the simplification effort will carry on forward, right? Now the simplifications effort in terms of pinch hole will focus on both from them and high temp. Then we'll compare and quantify how good it is a simplified approach, right, compared to the detailed approach for both high temp and high temp and room temp dynamic warpage predictions. And also the final one will be the call out location impact to the socket warpage, right? So in phase one, we just have call out and without call out, but we haven't looked into details on where to place the call out locations. So we are interested to look into detail on this call out location for phase two. And the final one is to provide some guideline and recommendations on the socket warpage measurements. So with that, this hopefully will help share and give an audience and high level on the phase two objective and also the scope. So again, the same material set that have been carried that we selected since phase one will be carried forward into phase two, right? So that we can have in-depth analysis regarding these three candidates. And this point is basically talk about the potential call location that, as I mentioned, in the phase two scope. So in the phase two, we plan to use a simulation, right, to have upfront process optimization to decide where is the optimal location or position to place the call out design, right, in order to reduce the shrinkage of the socket and also to reduce the socket warpage. So after the modeling optimization has been done, then we'll get our partner, right, FID, to build the socket and eventually to validate, right, the observations or the predictions from the simulations. So, and the final point is talk about the schedule, right? So these are the three major highlights of the phase two. The first one is the modeling methodology improvement. The second will be the high temperature dynamic warpage predictions. And also the third one is the call out design effect. So basically talk about where should we place a call out, right, in order to reduce the shrinkage and also the socket warpage. So the overall study is estimated, right, to complete at the end of Q4 this year, so that we can have a report out on the finding from the team effort. Then the last page I have is a resource requirement. Since this project is a continuous from phase one, so basically we have agreement, right, from the existing team member. So far, I think we don't see any concern or major gap in terms of the resources, manpower, or the sample build or the material supply. So basically, everything seems to be okay, right, for us to move into phase two. So I think with that, I think I have concluded the project detail sharing. So Haley, I would like to pass back to you so that you can continue.
Yeah, thank you, Chongken. So about how to join the project, as mentioned, iNEMI membership is required. It's quite simple. If you are already a member, if you would like to join, you just review the project statement of work and also the project statement agreement. That's the two documents are available on the iNEMI website that you can download. You need to, for each company, there is only one document need to be signed for the project statement. Okay, representative of the participant one should be enough to sign the signature page, and also need their management to be agreed and to sign as well. so that to make sure that the participation and resource are supported. Once you finish that, just send the scanned copy to iNEMI to me as that's fine as well. After we receive that, Grace O'Malley, she's the VP of Operations, will review and sign as a acceptance approval. Okay, that will accomplish the sign up process. The sign up due date is on February the 17th. We after that, with the signed members, this project will move forward to the execution stage. So if any company who are not a member, if they are interested to join, you can communicate with me or any iNEMI staff in the field to talk about the membership, the participating opportunity, so we can discuss that offline. So that's about how to join. I think we will open the floor for question and answers if there are any, either to the participation or to the project itself. Okay, there is a question from Jeffrey asking if the solder ball will be removed for socket warpage measurement. Zhongfei, you want to comment?
Yes. Okay. Yeah, I think I can answer that question. So for warpage socket warpage measurements, right? So we will validate at 2 stages. So first of all, it's a bare socket. So for phase 1, we always focus on bare socket, I mean without solder ball or pin. So that's the first step. So in future, right, as we establish a good correlation between measurements and modeling, right? So we'll try to predict more complicated behavior of the socket, right? Yeah. Hope that answered the questions.
Okay. Any other questions or comments? You also can unmute yourself to speak out.
Yes, you mentioned the high temperature warpage dynamic warpage measurement. How high during the assembly process? Because I'm thinking the low temperature soldering process will be included in the future for large size package.
Okay. So I think at the moment we are targeting a typical SMT reflow temperature. So the maximum temperature that targeted is 260. Yeah. So the dynamic warpage will collect up to 260. Yeah. So eventually, if low temp solder, right? So we also, because it's a dynamic warpage, we collected few data point before the socket, right, reached to maximum 260. So we'll have that data point in between as well. Yeah.
Okay.
Yeah.
Well, the question above I ask, we have experience if we remove the solder ball from the socket for warpage measurement. After the solder ball is removed, the plane on the socket will be changed. So that's a reason we cannot use the shallow array method to measure the dynamic warpage. But if we don't remove the solder ball from the socket, we have used another method called projection array. So we will compare these two methods in this phase 2 project. Projection array and the shadow array.
Yeah, in fact, we have both Incidix and Acrometrics on that. So yeah, they both do the measurement on this project. And regarding the solder ball removal, I wonder if Ron, you want to comment on that?
I'm unaware in my experience that removing the solder balls, I guess it depends on how you're removing them. If you mechanically polish or grind them off, or whether you thermally reflow and wick the solder away. It's not my experience that I've seen a change, but to be honest with you, I haven't explicitly ever checked before and after. In regards of comparing digital fringe projection to Shadow Array, again, as Haley stated, we have both Acrometrics and Incidix providing characterization support, but I think they're both using DFP technology. So DFP has the advantage over Shadow Array that discrete displacements in the vertical axis don't cause any real issues. So I don't know that we're going to compare Shadow Array to DFP because we're strictly using DFP.
It's from Acrometrics.
Yes.
Okay. Yeah, where your user?
I believe it's an AXP 2.0 system with DFP capabilities.
Okay. Yeah, that's my concern. Yeah, good.
Okay, any other questions, comments, or suggestions?
I have another question about test vehicle. The circuit size is about 50 by 50. But so far, the major concern will be around 100 by 100. It's possible you have a capability to produce the large size circuit around 100 square.
Yeah, Chunken, you want to comment? In fact,
Yes.
we discussed
Yeah.
this. Yeah.
Yes, it's a good question. So the 100 by 100 will be our long-term goal, right? Because at the day we do have some gap that observe, right? As I mentioned, we do observe that the warpage precision discrepancy, right, between the modeling and the warpage, the measurements. So we would like to address the fundamentals challenges first before we jump to the larger form factor. Because as you know, as we move to the larger form factor, the pin count will increase significantly. So that itself will impose another challenge to address as well. Right. So hopefully that will answer your question. Yeah, definitely we will focus on 100 by 100, but it may not in phase 2, right? So because we need to address the fundamental gap first. Yeah.
Yeah, yes. Yeah, that's the right approach.
Yeah. Okay. Additional comments, questions? Yeah, if there are any further questions, you can contact me, and I certainly can communicate with the project team. We can communicate later on those if you come up any later on. Okay. I think if no further questions, then thank you all for joining this webinar. I hope we have the opportunity to collaborate in this project, or maybe in a later phase or other projects. Okay. Thank you all. Thank you, Chungken.
Okay, thanks, Ellie, and
Have
thanks
a nice day. This evening.
Goodbye.
Bye bye.